Now we are starting a new chapter on the applications of Schwarzschild lemma. But depending on the topic, I'm gonna describe more background and more interesting stuff. And then at the end, I will tell you one applications by using the Schwarzschild lemma. Do you remember this lemma? It's about the polynomial of small degree, and you can find some assignment where polynomial is non-zero with some high probability. Anyway, so let me talk about the communication complexity. So motivation is somewhat interesting. So you have, let's say you have Earth and Mars, right? So you have a person A in the Earth and person B. So typically we call Elise and Bob. And now they are trying to solve some problem. But the input is given to both of them in a certain way. And then the question is something, right? For instance, Elise has some book and Bob has some book of the same one. And they want to make sure whether or not these two books are same. So for instance, on Mars, maybe there's some robots with some compute code inside, and people in NASA on the Earth want to check whether this compute code is not corrupted. So they want to know whether or not their code is same as the one in the Earth. Okay. The problem is that they can compute. Let's say the computer they have is very fast, but the only issue is the communications. The communication is so slow, right? If you want to send one bit to Mars, even with the speed of light, it takes several hours. Right? So this kind of study, the study of the complexity regarding communication, is the communication complexity. Right? So we typically make a communication protocol right? So the Alice and Bob already have predetermined protocol, kind of an algorithm to do what they're gonna do, right? Given the input, how they send the messages or not, right? And the complexity, so this is like a set of rules describing how Alice and Bob would exchange informations in what order. Right? And each communication is sending 0 or 1, right? So let's say protocol may say Alice will send 0 or 1, and then once Bob receives it, Bob does something, or maybe Alice send maybe many more bits, and then Bob says something. So this is a set of rules. And what is the complexity then? The communication complexity of a problem is a minimum max. Okay, so let's say it's the number of bits required transmitted until at least, okay, let's say Alice or Bob determine. Alice or Bob can determine the answer. For some technical reason, we don't require both Alice and Bob to know the answer because, for instance, once one of them has an answer, they can just send one bit, right? If the answer is yes or no, right? Then if let's say Alice now knows the answer, then Alice can send just one bit to the Bob, and the Bob also knows the answer. So it's just add extra bit, and we don't need that for better analysis. We don't require both of them knows the answer. Only one of them knows the answer. And this concept was introduced by Yao in 1979. So how do we formalize that? So A1, A2, AN be the list of, these are the list of possible inputs to Alice, and B1, B2, and BM are the list of possible inputs to Bob. All right, and then we construct a matrix. So let's say Cij is the value, let's say 0 or 1 for simplicity, and this is the value that they want to determine. The goal is to determine Cij when Alice has AI and Bob has BJ. All right. So Alice has input AI and Bob has input BJ, and the answer is 0 or 1. Right? And the problem is to determine what is the value, like this value, depending on the input of Alice and input of Bob. Right, so that's the problem. So the complexity, communication complexity is the minimum number of bits to be exchanged in order for Alice or Bob to determine Cij. So we need the sum notation. So let C be this matrix of Cij where I is from 1 up to n and j is from 1 up to. So this is a matrix. So this matrix is called the communication matrix. So it's a 0-1 matrix. So we have a matrix, and Alice knows the row and Bob knows the column, and the question is, what is the entry here? Right? So let kappa of C be the minimum. Okay, I should say in the worst case. Right? No matter which input Alice and Bob has, you can determine Cij by certain number of bits. That's the communication complexity. And the kappa C is the minimum number of rounds or bits Oh no, that's not kappa C. Okay, let's see. Yeah, communication complexity C. Okay, I don't know whether you like it or not. So CC, communication complexity of this matrix C. All right. Now let's see some commentary description of communication complexity. So depending on the protocol, Alice or Bob, I mean some other, Alice would send 1 or 0. And let's say you can determine the answer with k bits. What does that mean? That means we have some protocol where Alice send 0 or 1, so that partitions the possibilities of the rows. And let's say Bob sends 0 or 1, that gives me a partition of columns. And then maybe Bob sends again, so that gives me another partition of the columns, maybe on his side or that side. And then Bob would at least may send something, so that's giving partition of something. So eventually, if I can answer the problem with k bits of communications, then we are able to partition the columns and rows with rectangles, right? Some submatrices, and inside each submatrix, answer is all same, right? All 1 matrix or all 0 matrix. So in other words, this, okay, I mean, yeah, let's use 1 letter instead of CC, kappa. So combinatorially, kappa C is equal to the minimum number of rounds in order to partition C into almost homogeneous matrices. Okay, and what we do is where in each round we can split each of the current submatrices into 2 vertical, okay, 2 submatrices vertically or horizontally, right? So maybe I start with this, maybe at least partition like this, right? So their protocol says 0, that means here. More precisely, it's, I mean, they don't have to be consecutive. Maybe red part is here and blue part is here, right? So red means Alice send 0 and blue means Alice send 1. And then Bob can guess if it's 0, that means Alice's answer is in the red side. If Alice sends 1, then Bob can guess that Alice's answer is on the blue side. And then maybe if it's blue, then Bob would partition it. Maybe no, if it's blue, Bob would partition. Bob would partition this blue matrix maybe here. So this is like Bob would split this matrix vertically, but maybe protocol says that protocol may determine that, oh, if Alice send the red one, then Alice send another one. So that means Alice would partition this submatrix is horizontally, or this one horizontally, right? These are the same matrix, part of the same thing. So let me simplify the picture. So you start, this is round 1. So now I have 2 submatrices, 2 rectangles. And then round 2, I partition maybe the first one like this and the second one like that. Right, depending on the protocol, maybe if the answer is below, then Alice would send another bit. If Bob send another bit, then we are partitioning by vertically. And then in round 3, maybe Bob would again do this thing, but depending on the situation, maybe this thing and this thing, this thing. So each rectangle we are partitioning, right, at any time. So we are partitioning a matrix in k rounds, when each round you partition each submatrix into 2 submatrices, horizontally or vertically. So the goal is to minimize number of rounds in order to partition into almost homogeneous matrices, where the almost homogeneous means right. So what is almost homogeneous? Yeah. So that's the status where Alice or Bob knows the answer. A matrix is almost homogeneous if each column vector is all 1 or all 0 vectors, or each row vector is all 1 or is on or 1 or all 0 vector. So what does that mean? So for instance, this is 0 and that's 1, right? Or you have many combination, right? So 0, 1, 0, 1. So these kind of matrices I call almost homogeneous. Why? Why is this matrix useful? That's because if we have such a matrix as a communication matrix, then at least one of the 2 people, Alice or Bob, already knows the answer. In this case, Alice knows the answer because Alice knows where the input is, right? She knows the location of the row, and then the answer is the same. In this case, Bob knows what the answer is, right? So you don't need any extra communications. So that's why instead of partitioning all the way to the homogeneous matrices, we are partitioning it all the way to almost homogeneous matrices. Okay? And that's exactly the same as the communication complexity. So this is combinatorial description of the communication complexity given with the matrix. Now, from this interpretation, we should be able to deduce the following. So this trivial protocol. What is the trivial upper bound? Well, the thing is, so Alice has n possible inputs, and she can just tell what the input is, right? So by Alice sends n to Bob, and this requires log to n bits. All right, and then Bob will immediately know the answer. So this means that kappa of C is always at most log of n. Now, of course, it's also log and most log of m. Right. This is trivial upper bound. And if you look at this combinatorial definition, this is like dividing a matrix to like row vectors, right? So you have a matrix with n rows. You keep partition matrices so that all the submatrix will now only have one row only. That requires log n rounds. Right? So that's trivial protocol, so trivial upper bound. And we will talk about some lower bound and upper bound by using rank function of the matrix C.